and I'll be presenting my research proposal titled Recommendation on the Optimal LINAC Commissioning and QA Collimator Angle Selection and Frequency based on LINAC-specific radiation isocentre variability, and my supervisors will be Dr. Pejman and Dr. Hans. So just a quick outline, I'm going to give a quick background on what the radiation isocentre is, and I'm going to walk you through my proposal, and then I will have references at the end, so that's where all the references are for the images that I've used. So just a bit of background. So what is the radiation isocentre? So it's defined as the intersection of the central axes of planar and coplanar radiation beams. So if you guys can take a look at picture, the bottom picture, A and C. So this is just an example of what the planar and coplanar intersections look like. And in theory, much like the mechanical isocentre, it should be a single point in space, but in practice, it's a spheroid because of all your mechanical uncertainties. So the size of your radiation isocentre, that would be the radius of the smallest circle that will inscribe all of the central axes. And so if I draw your attention to picture B and D, top right and bottom right, we can see that if we compare the images, the central axis would be the midpoint of each of the fields. And once we've actually extracted all of this, the central axes, we'll basically try to inscribe the smallest circle possible that will intersect all of the central axes, and the midpoint of that circle would serve as your reference location for your radiation isocentre, and that's the point that is used in EBRT. And just to put things into context, for SRS and SBRT treatments, the tolerance value for the radius would be 1 millimeter. And for IMRT and non-IMRT, the tolerance will be 2 millimeters, and this will be given in task group 198. So some factors that would affect your radiation isocentre would be mechanical variations within your LINAC. So examples could be the beam transport system throughout the bending magnets, your steering coils, your focusing coils. Those could alter the trajectory of your beam ever so slightly, and that would affect how the beam actually strikes the X-ray target or the beam focal spot. If flattening filters are used, that could also affect your radiation isocentre just because of your slight deviations within the machine itself. And gantry sag as well. As the gantry is rotating around, gravity will cause the frame to sag just ever so slightly, and that will affect your radiation isocentre as well. So how is it actually measured? Usually it's done either through film or EPID images. Film is not recommended to be used anymore, just because of the advent of your SRS or SBRT stereotactic type treatment techniques where your tolerance values is 1 millimeter, and it's hard to actually measure it by eye if you're doing it on film. And even if you do convert it digitally, there will be distortions, so it's best to use EPID going forward. And there are two types of tests to actually draw the smaller circle. There's a Winston Lutz test and a starshot test. For my project, we will only be concerned with the starshot test. And again, the starshot test is shown on figure B and D, where you can see that the central axes kind of look like stars, and we're going to inscribe the smallest possible circle. And the image on the top right is just to give context as to why the radiation isocentre is important. So you can see on the top for HA, that's hyperarc, or at the bottom, it's rapid arc or VMAT. So we can see that for all the gantry and collimator rotations, slight deviations, especially for stereotactic therapy, that will affect the conformity. Okay. So with that background, I'll just give a quick update about the current status of this project. So the data was provided by the Department of Oncology at Odense University Hospital in Denmark. The first measurements were done in July 2015, and a second batch was done in February 2018 on the same 8 LINACs. The measurements were done in intervals of 30 degrees, so the collimator and gantry angles were rotated from 180 degrees to -150 degrees, and for each gantry angle rotation, the collimator was rotated throughout. So we can see that that would give us 144 images per LINAC. And for each LINAC as well, 6 MV and 18 MV beams were measured, and flattening filters and flattening filter free beams were measured as well. So we have quite a bit of data. The data was cleaned by a previous student called Yi Heng. So this project is an extension of his, where his project was basically the cleaning of the data and presenting how the data looked like. But my project going forward would be to do analysis on that data set and to draw meaningful conclusions from that. And that we can see there, the verification and analysis for the clean data, and then extracting any features, and then doing modeling and extrapolation of the end result. And we can see here on the table, radiation isocentre quality assurance is an annual process. And if we look at the bottom, it says coincidence of radiation and mechanical isocentre. Again, we can see the tolerance for non-IMRT, IMRT, and SRS treatment types is 2, 2, and 1 millimeters respectively. And this can be found in task group 198, which is an update of the task group 142. So my research aims, firstly, is to investigate statistical methods to analyze the variability of the different LINAC-specific radiation isocentres. So it's a hypothesis at this point that each LINAC will have their own unique angles that will give larger deviations for radiation isocentres. So through this research, I'll be investigating the different collimator angles, gantry angles, and trying to find a relationship between them to see if it's unique or not, or if I can draw any correlations that are useful in extrapolating from that. And then secondly, I'll be developing predictive models. Again, once the statistical methods to analyze have been developed, I can then extrapolate that data and predict, or at least try to predict, at which angles what deviations would occur for the radiation isocentres. And as we know, this is particularly important for treatments such as VMAT for the prostate, for example, where if you have certain angles that deviate, that cause larger deviations of the radiation isocentre as compared to others, then your treatment may not be reflective of what's actually happening. So it's good to model that in. And then finally, to publish the data and results, and the paper would be a recommendation on the optimal angle selections based on your LINAC specific parameters. So when a LINAC is being commissioned or an annual QA is being done, the larger deviations can be determined. And then going forward, instead of using the standardized cardinal angles, which may not capture those larger deviations, those optimal angle selections based on that LINAC can be implemented so as to get better calibrations and conformity. And lastly, if time permits, I will be trying to implement this clinically, which is basically implementing the extrapolated model and tracking at the different control points during ARC techniques, such as VMAT, and then model that within the TPS or treatment planning system to see if the dose distributions have changed much at all, and if there's more conformity that can be achieved. So for methods, firstly, I'll be conducting the Starshot test within MATLAB. The code is ready to go. It's been written by Pejman. And so to conduct the starshot test, we'll have to use Gaussian filters to reduce the noise for the DICOM images that we have, and then we'll evaluate the central axes for the beam data. And if you see on the right here, we can see that as we progress from A through to E, we'll be slicing the image, and the profiles, we will try to match the edges, and then extrapolating the midpoint of each of the slices. And then once all the slices have been collected, we will combine all the midpoints, and that would give us the central axes of the radiation field lines. So that would allow us to, again, as I showed in slide 1, get the minimum radius circle. That would give us the radiation isocenter parameters. So you'll get your radiation isocenter size, the angle correspondence, and the LINAC type, and beam energy as well. There's a potential at this stage for converting the code into Python, because that's what I'm more comfortable with, but we'll have to see going forward if that's the most efficient way of doing things, or if we should be sticking to MATLAB. And then the second part would be investigating the potential statistical methods that will allow for the extraction of meaningful information. So at this point, we will have to get the data out before we can do any sort of modeling on it. So that would be the next step. So we'll be doing some curve fitting, and from the curve fitting, we'll have to see if it's statistically relevant, and if it is, we can try extrapolating that and then building a predictive model on that to predict angles that we may not have. And if, for example, we were to conduct experiments or QA with LINACs in angle sizes of 1 degree difference, that wouldn't be very practical. So this model would try to address that. The significance of this research would be the better execution of VMAT or stereotactic techniques, such as SRS Sabre, HyperArc, and VMAT. And another one would be bespoke collimator and gantry angle selections for the different LINACs. So each LINAC would have their own mechanical uncertainties, and if we were to optimize the selection angles that we determine during commissioning or during the annual QA, we can better calibrate those LINACs for treatments down the track, and this reduction in uncertainty will give us better dose conformity and lead to better treatment outcomes. And as the second part of this research, if I do get to the part of clinical implementation, this will allow improved tracking within the TPS, because if we can model the radiation isocenter variability and shifts within the TPS at different control points, we can then better adjust our doses for dose conformity. So an example of that would be this picture on the right, where it's a VMAT plan for the head. If I could just draw your attention to the top right and the bottom right of the image. I'm not sure if it's big enough, but you can. We should be able to see a little thin slice of pink in the brain that looks like a pancake. That would be your hippocampus, which plays a major role in your learning and memory. So at the top for the original plan, assuming perfect radiation isocenters and mechanical isocenters, we can see that the dose is quite conformal, and there is a lot more sparing of healthy tissue as compared to the simulated plan at the bottom, with margin setup errors of 2 millimeters and 2 degrees in each direction. And we can see that the dose is actually crept up a lot closer to the hippocampus, and this is a problem for the patient, because that's an organ at risk. So the benefits of this research would be greater awareness of the uncertainties involved with radiation isocenters, and optimized protocols when calibrating for it and when doing commissioning and QA. we get more conformity of dose, so a reduction in your PTV, and therefore increasing your therapeutic range, because now if we can track the variability in the radiation isocenters, we can better plan for the shifts and irradiate less of the healthy tissue and conform the dose more towards the lesion. And this would hopefully lead to better patient outcomes and better stereotactic techniques. And this is my research plan. So at the start, I'll be getting all the raw data for the collimator and gantry angles. We'll be extracting the central axes and processing all the DICOM images. And through that, we will get all the radiation isocenter parameters, of which we can do our statistical analysis on for the feature extraction. So firstly, we'll have to decide how the data looks like and how we would represent the data in a meaningful way, and then model that statistically to see if we can fit a curve against it. And if we can, then I will come up with a predictive model that will be an extrapolation of the data points that we have, and then publish the results for any recommendations on the optimal angle selections and what the model actually represents. And hopefully we'll have enough time to implement it clinically, to test it against LINACs at Sir Charles Gardner, implementing the model into TPS to model the effects and to see if it is comparable to what's actually happening in real life. And then I just have a Gantt chart here just to give things into perspective of my timeline. And these are my references. Thanks for listening. Does anyone have questions for me?
Okay, thanks, Zhen. Any questions from them? Yes, Michael.
Hi, Zhen. You won't know me. My name's Michael. I'm from Newcastle. So thanks to Pejman for the invite to these talks today. Great to see
Michael.
you and you, Nasheed, and you too, Martin.
Hello.
Quick question for you, Zhen. Thanks for the talk. With your predictive model, is there an underlying assumption there that the radiation isocenter is stable over time?
Yes. So according to TG198, it's assumed that once the radiation isocenter has been determined for a particular LINAC during commissioning, it should stay stable for the life of the LINAC. And that would be an underlying assumption. And again, because the amount of data that we have is all it's not a live measurement. We're just getting data that from years ago. We wouldn't be able to know what circumstances those LINACs were measured under, because there will be day-to-day variations and whatnot. So if there is time, that's definitely an avenue that I would like to explore. But for now, yes, that would be an assumption.
Okay, thank you. I would just be a little bit wary of that assumption. I think radiation isocenter can change over time. So just be a little bit wary of that assumption. But thank you.
Thanks, Michael.
It's a really good point. Yes, probably we need to go with some repeatability for some measurements. We can ask Hans, or we can do here to see how much change we have in radiation isocenter. Especially after any adjustment or repair to the gantry head, definitely things are changing. So that's great. Any other questions? All good from Zhen? It's great. Thanks very much, Martin. If you can please stop recording.